Uniform circular motion. I'd like to introduce you to uniform circular motion in this video. What I mean by uniform circular motion is this. So this is moving in a circle, as you can see. When we're saying that it's uniform circular motion, I'm saying that the movement is not getting faster or getting slower, but it's staying at the same speed. So it's uniform circular motion, or uniform angular motion is another way of saying it. Now, when we're considering this movement, what we can look at is a number of aspects. First of all, angular displacement. Now, by angular displacement, I'm talking about how, what angle this moves through as it is turning. So we can measure that in various ways. First of all, we can measure it in terms of revolutions. So when we're talking about that, we're talking about how many times it spins around. We can also measure this in terms of degrees. So, for example, if it goes around in one circle, it's obviously moving through 360 degrees. Now, another way of indicating how far it's moved is what is called radians. Now, when I use the word radians, what I want you to think of is the word radii, or radius, I should say. Radius is singular, and radii, rather than radiuses, is plural. Now, when we're looking at radians is an angle. It's an angle. If I draw a line from this here, like this is one radius, if I get this length and measure it across here, so this length here is one radius, then the radian is that angle there. Excuse me. And it's about 57.3 degrees. If we get another distance here of radius, okay, and mark that there, then another one, radius, another one, another one, another one. I can fit almost 6, well, can fit 6 and a little bit more. Here's a little bit more. Now, you may recognise this as related to pi. What we've got here is, in fact, 2 pi of these. So it's 2 by 3.14 round about 2. So we can talk about the number of radians, we can talk about the number of degrees, we can talk about the number of revolutions when we're saying how far something moves in a circle. It's angular displacement. Now, there is a symbol for the number of radians, and it's this, theta. So when we're seeing theta in this context, it's radians. It's not degrees, it's not revolutions. This is angular displacement. So the next thing we're going to have a look at is angular velocity. And so what we're looking at here is how fast something is moving in a circle. So when we're looking at angular velocity, again, we've got various ways in which we can measure that. First of all, there's the number of revolutions per second. There is the number of degrees per second. And then we've got the number of radians per second. So all of those are ways in which we can measure angular velocity. Now when we're looking at that, one of the reasons why we go with radians when it comes to circular motion is that if we know the number of radians, it is very, very easy to work out two things: the displacement, the distance travelled, and how fast it's going. In other words, the instantaneous velocity. Now when I'm talking about that, what I mean is we can work out how fast something like this valve here is moving, or how fast this is moving in meters per second. That is, if we know the number of radians, or radiuses, radii, per second, and we know the radius. So when we look at this, you can see that the little bit of white paper is moving more slowly than the valve here, this little black thing. That black thing there is called a valve. So as that spins around, the number of meters per second that this is moving in is actually greater than the number of meters per second. So when we're looking at that, we're looking at what's called the instantaneous velocity, or we're looking at the speed at which it is travelling. So either of those two are handy things to keep in mind. And this is the reason why we use radians, is that if we know the number of radians per second, we know the number of radii that this is moving around per second, the number of radii that this is moving around per second, we multiply those radii by the radius, and we can actually work out how fast it's travelling. Now, to put our angular velocity into some sort of formula, the expression that we have, or the symbol for angular velocity, is this one here, which is called omega. Now, omega is the lower case for this Greek letter. As you might be aware, omega is used in electricity, and it's the uppercase for the Greek letter there. So we don't need to be confused about that. So the angular velocity is saying how many radians. Remember, this is the symbol for the number of radians per second. Now, if we want to know how fast something is moving, as I mentioned to you before, what we can do is quite easily work out how fast it is moving. And I'm going to use the symbol V there for velocity or speed. That's going to be equal to omega times r. So this is the number of radiuses that it's travelling per second. This is the radius, and this is the time. So that will give, as I say, how fast that object on the surface of the wheel, for example, is moving. Now, another situation which I want you to look at is this. Let's say we've got 10 revolutions in 5 seconds. Tell me, what would be the period? The time taken for one revolution. If we've got 10 revolutions in 5 seconds, the period would be 5 divided by 10, which of course would be 0.5. What units? Period, time, seconds. Now, another question. What would be the frequency? be the frequency if we've got 10 revolutions in 1 second. In other words, how many revolutions per second? The number of revolutions per second for each second would be 10 divided by 5, which would be 2. Units. Now, units would be either cycles per second, we could say cycles per second. The other thing that we can say is hertz. Okay, that's another symbol for cycles per second. Now, can you see any connection between the period here, T, and hertz frequency? 0.5, 2. You've got it. Yes. It's the period is equal to the reciprocal of the frequency. Now, I want you just to think for a moment of one revolution. Okay, so one movement in the circle there. And the time taken for it. Well, the time taken for it, we've come across that before, is the period. How far does it move? Well, what angle does it move through? How many radians in one revolution? 2 pi. So it's moving through 2 pi radians in one revolution. This is what we call the angular velocity. How many radians per second it moves through. The other units for angular motion are, of course, revolutions per second or degrees per second. Well, we don't think about degrees per second. They're pretty useless. Not that I've got anything against degrees, but okay. So one of the things which I said about radians, so this is the number of radians per second. When we think of the word radians, think radii, radiuses, if you like. So we've got 2 pi radiuses in that period of time. So if we want to work out how fast something on the edge of something like this is moving, in other words, its instantaneous velocity, then all we need to do is multiply this figure by the radius. Go through that again. This is the number of radians per second, or the number of radii per second that it's moving. So it's the length of the radius. How many of those each second? So we can say the instantaneous velocity, or the speed, is 2 pi r over 2. Okay, so this is the radius. We're saying this many radians, this many radii per second. What unit would we have here? Because that, assuming it's meters, we have meters per second. So this is a measure of the instantaneous speed, instantaneous velocity, or the speed. Now, another way we can think of this, remember what we said a moment ago, that period is equal to 1 over frequency. If I substitute in here for frequency, for period, if I put this in here, for period, I'll get this speed or velocity, this instantaneous velocity, to be 2 pi r times the frequency. So we can, yes, so that's it. The other expression that we can keep in mind for the instantaneous velocity is this one. The angular velocity times the radius. Remember what this means? This means the number of radians per second. What we've got up here. So the number of radians per second times the radius is going to give us the speed in meters per second. So when we look at this, we've got these expressions here for the velocity, and we've got a number of other expressions, matching expressions if you like, for the angular velocity. So we've got angular velocity is equal to 2 pi on t. We've got the angular velocity is equal to 2 pi f. And we've got the angular velocity is equal to the number of radians divided by the time there. Now this time here is not to be confused with the period. So we've got these expressions for angular velocity. We've got these expressions here for the instantaneous velocity. So that's our second aspect of circular motion. Now another aspect of circular motion is acceleration. We've been talking about uniform velocity, uniform circular motion I should say, uniform velocity. And acceleration is going to be the subject of another small video, but in the meantime what you can do is have a look at worksheet number 9 and have a go at those questions.